Hello and welcome to today's webinar. My name is Tyler Reid. I'm the Manufacturing Applications Manager here at GoEngineer. And today's topic is something a little bit out of my normal wheelhouse, and that is simulation. Specifically, we're going to have kind of a practical discussion about finite element analysis and topology optimization. So I came up with this idea for a webinar because it's a question that we are asked fairly often. Simulation is a tool that we have been selling under the SOLIDWORKS brand for years and years. But topology optimization has been a technology that hasn't really been on the radar until the last, kind of 2 years or so. And as we started talking about topology optimization and shape optimization or generative design, whatever you want to call it, the question always seems to be, does this replace FEA? Do I need this and my finite element analysis? Is this a replacement for simulation? So I figured we'd kind of have a practical discussion about it. I say a practical discussion because this webinar is going to be fairly simple. It's going to be more about kind of a broad view of FEA versus topology optimization. We have plenty of content going over how to do, simulation, static, dynamic, linear, nonlinear, thermal, fluid. We have it all. And we also have how-to videos covering topology optimization. So that's not what this is. This is going to be a comparison and a discussion of where each one fits within the design workflow. So to start off, we're just going to cover the basics of what each one is. So FEA, finite element analysis, it's essentially a numerical method for solving physical problems. Those problems can be structural. They can be in fluid states. They can be heat transfer. They can be a wide range of things. The idea behind FEA is that we're taking large problems across, an expansive domain, and we're breaking it into smaller, simpler problems. We call those elements or finite elements. And the idea being that if we can come up with a series of small solutions and assemble those into a larger system, then we can solve very complex problems using simplified mathematical algorithms. One of the unique things about finite element analysis is that we're able to hone in on local areas of interest using mesh controls and things like that. We'll be talking about that. One of the big deals here is that FEA outputs values. So we feed it a 3D model. We set up constraints or boundary conditions, and it outputs things like stress or strain, factors of safety, displacement values, and it maps those results over a 3D shape, but the actual results can be delivered in a text file, and they're numbers, they're values. So we talked about these finite elements, and I mentioned the word mesh. On the image on the left here is a 3D model that has been meshed, and what we mean is that it has been broken up into smaller three-dimensional shapes that have things called nodes, and those nodes are where the calculations are taking place. In this image, again on the left, we have some green arrows, we have some purple arrows. Those are boundary conditions. We call those fixtures or connections. These are also things like loads, forces, torques, pressures, heat changes, things of that nature. The result is that same shape, but with numerical values applied to it. So in the image on the right, it happens to be a displacement plot, and it's showing that different areas of the model are displacing a certain amount. So as a designer or an engineer, I set up these simulations primarily for verification, okay? I run a simulation, I take a look at the results, and me, as a person, use my experience to make some judgments. So the workflow for FEA kind of starts with this initial design. I call it a first guess, and that first guess as to what the part should look like is kind of based on my own personal experience, or sometimes I'll look for prior designs, things that have worked in the past. One of the downsides of that is I have a bias, what have I personally done in the past, or what have other people done in the past? So it's very hard for me to come up with novel or unique or new designs this way. But I come up with this first guess, and then I set up a simulation study. So that involves, selecting the correct material or materials if we're in an assembly, creating things called connections, where are my bolts or my fasteners, where are my joints going to be? If I have parts that are touching each other, are they bonded or welded together? Are they free to slip? Can they pass through one another? And then we also have loads, like I said, forces, pressures, torques, things of that nature. So I'm setting up boundary conditions, and then I'm also creating a mesh. And creation of the mesh can be an automated step. There are tools to do that, but it's usually something that me as the person setting up the study wants to have some involvement in. The results of my study are only as good as the boundary conditions, the accuracy of them, but also my mesh. We specify the type of mesh. We have solid meshes, we have shell meshes. We specify the shape. We have different types of mesh elements. And we also specify the size of the mesh. The size of the mesh allows us to control the detail of our results. And something that we're always balancing is the speed that those results are delivered in, and also the accuracy or the resolution of our results. So it's not uncommon to incorporate variable mesh sizes, or something in SOLIDWORKS we call mesh controls. And mesh controls allow us to spend more time calculating results where we need them and less time where we don't. So in the cube here, we have a finer mesh control applied to the edges of the model, and then the faces around, and the open cylinders. And the reason we do that is because those are areas of concern. Those might be places where we suspect there could be stress concentrations. They might be areas where we are, incorporating a press fit or a bearing. But we don't want to mesh the entire model that size, because it would just take an inordinate amount of time and kind of unnecessary resolution. Once we have the simulation set up, we run it, and then we evaluate the results. So right away, we are asking ourselves, do the designs fail? And if they do, when do they fail and why? So this is at first kind of just an either or thing. Does it fail? Yes. Or does it not? No. And if it doesn't fail, then the next question is our design optimal? And that can mean a lot of different things. What we are trying to look at is the results to check if there are any areas where maybe the part doesn't see any stress or strain. If there are areas of the part that are stress-free, then technically we might not need those areas in the model at all. But it's not a very automated way of optimizing the parts. So what we do is we assess the results, we make some design changes potentially, and we call this iterating, and then we run through the simulation again. But I'm always relying on me and my personal experience to, set up correct studies, one, but also to be able to read the results. And reading the results and making good design decisions based on the results is a difficult thing to do. So that's where topology optimization comes into play. It's not an either or question when we are looking at FEA and topology optimization. Topology optimization is a simulation-driven design tool. So FEA is actually incorporated into the topology optimization. If we didn't have FEA, we wouldn't have topology optimization. You can't have one. You can't have it without the FEA. What topology optimization is allowing us to do is to kind of develop a numerical approach to answering that question, is my current design optimal? We're using software algorithms instead of our personal experience to start removing unnecessary material based on our optimization goals. When we set up an optimization study, we are always setting a target or a goal. I want the minimum amount of mass, or I want the maximum stiffness to weight ratio. I want to work around certain resonant frequencies, potentially, okay? I want to minimize displacement in this area. These are goals, and what the software does is it runs through a simulation study, and then it starts to remove material trying to target these different goals. So I said before that the output of FEA is a value or values. And then those values are laid on, the same 3D shape that we fed into it. The output of topology optimization are load paths. So it's actually a new 3D shape. And what we're seeing is that based on the analysis, how it's set up, these are the load paths through the part. And how we can interpret that is because there's a load path here, we need material there. On the left, we have our what we call design space. This is a simplified 3D model. And there's some extra stuff going on here in this image. We have some bolts in there. Those represent fasteners. In this case, they are nuts and bolts with, maybe preload on them. We have in red a force that's offset from the face. So it's a remote force acting on the gray face, the gray curve face. And then in blue, we have a symmetry plane. This is in Solid Thinking Inspire, this is considered an extrusion shape control. So we have set up a simulation study, but the goal of our simulation study is not to just figure out the stress and the strain and the vector of safety. It's how much material can I remove while maintaining a certain factor of safety? Or what is the max stiffness to weight ratio if I reduce the mass by 70%? Something along those lines. And the output is a shape like you see on the right. So the workflow for topology optimization is a little bit different than FEA, but it incorporates FEA. So we create an initial design. This isn't our first guess. This is what do we absolutely need, we call these critical geometry. And then what's the potential work envelope of our part? So if I go back one slide here, this initial design on the left, in the gray, we have that curve face. That's a critical geometry. We know that face needs to be there. And then underneath those bolts, we have some cylinders that are also gray. And those are critical geometry because they're the mounting points for this bracket. In red, we have something called a design space. What we do is we model it up as the sort of maximum material condition for our part, okay? This would be the most material possible. And obviously this would be the strongest, it would be the stiffest, it would be all of that, but that doesn't make us a good designer to overbuild. We want a part that's nimble, that's lightweight, that is, high performing, so we want to optimize it. We set up our simulation study, okay? We're doing the same thing. We're selecting a material, we're making connections, we're setting up loads. Something that's a little bit different as opposed to FEA is we are also implementing things called shape controls. These are controls over the resultant shape, and they're usually based on manufacturing methods. So if we were to eliminate all shape controls, if we were just going to avoid implementing them, we would usually end up with a very organic shape. And if we are designing for additive manufacturing or 3D printing, then that might be a potential solution for us. But the vast majority of parts today are still manufactured in conventional ways, things like machining or casting or molding or extruding. And each one of those methods of manufacture are kind of geared towards different types of shapes. If we're molding or casting, we might need some draft in one or two directions. So these are shape controls. And then we choose a target characteristic. What is our goal? Okay, again, do we want to minimize the mass? Do we want to make it as rigid as possible for a given weight? Do we want to reduce or minimize displacement in a certain area? We set up a goal. We run the simulation study. It delivers a result. And then what do? We confirm that result with FEA. Okay, so it's going to give us a result. And going back a slide again. In this photo here, I've set this up in Solid Thinking Inspire, and the image on the left is considered the 100% material condition. And I set up a goal that said, give me the max stiffness with a 70% weight reduction. And so it reduces the weight 70% and then gives me, the most rigid shape for that possibility. But in my goal, I may have overestimated or underestimated how much material I can remove. Potentially by removing 70% of material, I end up in a situation where my factor of safety is less than 1. Or my factor of safety might still be 5.0. So I could actually remove more material. So we do end up iterating a little bit because we end up with a resultant shape, we confirm it with FEA, and then based on those confirmations, we don't really make design changes. All we do is we go back and we adjust our goals. So if I found that, at 70% reduction, my factor of safety is 0.5, well, I'm going to go back and I'm going to change my goal to maybe 50%. Now, some topology optimization software has, something called like a slider. So yeah, I say I want to target 70% material reduction, but it's going to deliver anywhere from 0 to 80%. And I just adjust the slider. I don't even have to rerun the study, which is very nice. So here's kind of what that looks like. We do run FEA typically alongside the topology optimization. We do it to confirm our results, like you see there on the right, but oftentimes we'll do it before we run any shape optimization at all. And the reason why we might do that is to answer the question, is there room for optimization at all? And there are scenarios where there's not. Sometimes we will come up with this initial design, and even with the maximum amount of material, we're still under a specified factor of safety. So then we actually have to go back and readdress our boundary conditions. We might need to rethink our part envelope entirely. That's usually not the case. Most parts do have room for optimization. And so we're using FEA to confirm shape results. Both images that you see here are done in Solid Thinking Inspire. Inspire is one of the tools that we do offer and we use extensively in-house here, and it has built-in FEA capabilities. So going back to the original question that we proposed is, FEA versus topology optimization, which one do you need? And ideally and also technically you need both. Now sometimes the FEA is invisible. If you're purely using a topology optimization tool, you may actually never see a conventional FEA style result. You might not ever see the stress and strain or displacement graphs. But most tools that do shape optimization incorporate some level of FEA. Ideally, you want to be using both because, as designers and engineers, I think most of us will agree that our parts have room for improvement, and sometimes those improvements are not intuitive. I don't know how many times I've been surprised to find the results of my shape optimization to look like something I would have never guessed because I'm always thinking in terms of what have I seen before. I'm not a genius. I'm not a design savant. I am a creature of habit and I learn by watching others. And I think that goes for probably 99% of us out there. So when we have tools that help us think out of the box, that's nice. But if you have it in your head that you can't use both, or for some reason you don't think you can fit both in your budget, then you might just have to choose one. And again, like I said, if you go with the topology optimization tool, they usually include some level of FEA, but what you have to do is ask yourself, what is the priority here? Do I need a design tool? Or do I primarily need a verification tool? If your primary concern is verification, then you may have to consider going with just a straight up FEA tool and foregoing topology optimization. The reason for that is, strict FEA tools tend to have more robust simulation capabilities. They're going to have more options to consider things like bolt patterns and sharing of forces among bolts, or different types of contact, bonded, not bonded, pretension, rotational stiffness, things like that, right? All of the nitty-gritty details that make or break a simulation. If you are not doing hardcore simulation and you're looking more for a design tool, then you're probably going to sway more towards something that offers topology optimization with FEA in the background to verify your results. Now, for the small but growing number of you out there that are designing parts for additive manufacturing and you're looking for some sort of simulation type tool, then topology optimization is probably going to be where you want to go, because especially for end use parts, 3D printed parts that are used in their printed form, there usually is some compelling reason that you need to print those. And many times that reason is you need to make the most out of the space. You need to lightweight it as much as possible. You need to create a shape with a stiffness to weight ratio that requires some organic, complex, lattice type structure that can only be created with additive manufacturing. And usually those complex shapes are the result of some sort of shape optimization. So I've mentioned Solid Thinking Inspire a couple times here. The next 3 slides are just going to go over the different shape optimization tools that we use here at GoEngineer, and then we'll wrap up this Friday afternoon webinar. Solid Thinking Inspire is a tool that we have been pumping out a lot of content lately. We love this product. It's been a great tool for us to develop 3D printed parts and help us consult in the design for other mechanical type parts, whether they're machined or cast or molded. Inspire has been around, and the technology behind Inspire has been around for decades. It is a very robust shape optimization tool that includes motion analysis and assemblies, has great shape controls so that you are not just going through the motions of shape optimization only to end up with a shape that's unmanufacturable. Something very unique about Inspire is that it has a direct editing tool called Polynerves that allows you to push, pull, and create very swoopy, organic shapes that are great for industrial designers and some adventurous SOLIDWORKS users, creating shapes that honestly we can't do in SOLIDWORKS. It will also do something called topography optimization. And this is more relative to things like sheet metal, thin parts that need to be stamped for extra rigidity. It does have FEA tools included, but I have to admit they're simpler than what's offered in the SOLIDWORKS suite. So it's going to be simple verification and comparison of results. And then typically you would export your model from Inspire to SOLIDWORKS to do all your detailed design, your finished design, now that you have the bulk shape, and also, potentially some further verification in the SOLIDWORKS simulation suite. So the next option that we have is the topology optimization within SOLIDWORKS. About 2 years ago now, SOLIDWORKS Simulation Professional started including some topology optimization tools, and in the last 2 years, those tools have improved quite a bit. Of course, those tools are supported by very robust FEA tools. This means, initial verification of your design space is going to be accurate, and also verification of your shape results are going to be very accurate. Of course, it's going to be a fully integrated solution, which streamlines your workflow. Recently, they did add shape controls to allow you to achieve, manufacturable results, which in my mind was a deal breaker. Without shape controls, shape optimization is pointless for 99% of people out there. One nice thing that you can do in the topology optimization tool is you can pair it with SOLIDWORKS design studies, and that allows you to very easily set up and assess different loading conditions. Those are the two primary software options that we use in-house and that we are, actively promoting to our partners in industry because we feel like they are the best positioned right now as, products ready for prime time, ready to be used today. But there is a third one out there that is growing on us. And although it's still in development, it's showing to be, pretty promising. It's called Desktop Metal Live Parts. And if you were at SOLIDWORKS World this past year, you saw a promotion of it. That was version 1.0. I think now we're in version 1.6, and the improvements are getting better and better, and the software is getting better and better with each iteration. It has an entirely different approach to topology optimization than the prior two pieces of software. Those two pieces of software, you would start with the design space and it's whittled down into shape. Desktop Metal Live Parts is a true generative design. It is creating shapes from things called seed cells. And I encourage you to look this up. There's plenty of content on YouTube and some white papers released by Desktop Metal. This concept of a seed cell that is growing and actually reacting in real time to dynamic load scenarios. While the part is growing, you can start changing loads and the part reacts. This is topology optimization and shape optimization taking even a step further. And in terms of trying to mimic nature, because that's how nature does. Bones grow in reaction to loads, trees grow in reaction to loads, and those loads are changing. A tree is reacting to loads that are changing day to day, season to season. And this is how this software is working as well. I haven't fully wrapped my head around the practical use of a constantly changing, dynamically loading situation. But again, I'm not a design savant. I'm not a design genius. I'm struggling to understand it. But I think there will be a day where this becomes the go-to design tool, especially for fluid domains and some other very complex situations. It is semi-integrated into SOLIDWORKS right now. We do all of the design in SOLIDWORKS, and then it outputs to Live Parts, which runs some calculations on the cloud and then spits back to SOLIDWORKS here. All three of those tools, we are happy to set you up with a trial. Some of them are easier than others, but we'd love to get your guys' hands on those tools because, at least me personally, I'm a strong believer in topology optimization. I do think it's the way of the future for design and engineering services in the future. Specializing in the creation of accurate simulation studies and then allowing software algorithms to make that first guess for the shape for you. So I want to thank you guys for joining. It's a Friday afternoon. I know it's not the easiest time to join a webinar, so I appreciate those of you who did join. And I'm always open to topics. So if you watch this and you have and some ideas for another topic, let me know. Shoot me an email or hit me up on LinkedIn. Appreciate it. Have a great weekend, guys, and I'll catch you next time.